The next major player in the organization of the periodic table is Dmitry Mendeleev. We're going to talk about his publications in 1869. Of course, he did some work before then, and he continued to do work afterwards. Mendeleev, by the way, is my style icon. So go look up some pictures of Dmitry, and you will see that I have some way to go to to match his stylistic facial hair. Anyway, at the time, there was over 60 elements that Mendeleev was aware of, and again, he was teaching chemistry in Russia. Um, and he, like any good teacher, was trying to illustrate to his students the elements that they knew and how they behaved and so forth. And so he started to organize them. Now, again, there were other scientists who began to organize them too. We spoke of Dobereiner, with his triads earlier, but Mendeleev discovered this. He saw that if he took the elements, which I have a bunch listed here, and he kind of placed them in numerical order by atomic mass. Now, again, they did not know about atomic number at the time, so you will not see the atomic numbers here, but you will see the rough, rounded atomic masses, right? So lithium has a mass of 6.9 something, right? But I'm going to say, well, it's close to 7. Beryllium has a mass close to 9, and boron close to 11, and carbon close to 12, and so forth. And so we listed all the elements in increasing mass, atomic mass, and the color of each element that I made in my little boxes represents the behavior of that particular element. There was lots of tests, it was a solid, liquid, or gas, was it kind of metally or not metally. We'll learn the difference between metals and non-metals later. How did it react, who did it react with, and so lithium behaved a certain way. And notice beryllium is a different color, so beryllium behaved differently than boron, than carbon, than nitrogen, than oxygen, and fluorine. But then sodium comes along, and we notice that sodium and lithium, they have similar behaviors. And so in my little diagram here, I have them both colored red. So he noticed something. He noticed that this pattern of behavior seemed to kind of repeat. Right? We have lithium behave a certain way. Then beryllium has a behavior, boron, carbon, nitrogen, oxygen, fluorine. And then if he continues, and again, this is by increasing atomic mass, then notice this pattern of behavior starts to happen, right? Sodium happens. And then magnesium happens. And then aluminum happens. And notice this pattern, silicon happens. The pattern, the colors just start to repeat in order again. Kind of like, well, before I say it, let me just kind of organize it. So what Mendeleev did, nope, that's not what I wanted to do. What he did, I lost it. I'll have to repeat. Okay, is he reorganized these elements instead of listing them all on the line like this? He kind of took them and rearranged them still by atomic mass, but also by property. And now it's starting to look like a table, isn't it? And what's important here is, wow, having a hard time today, that he had the properties going one way on the table and the increasing atomic mass another way on the table. So here on this table, I have the properties up and down, they're the same, and the atomic mass is increasing in this way. Now, Mendeleev's original table was reversed. Mendeleev had at one point it would have been all reds up top, and then the patterns of color would be repeating downward. But so I flipped the table 90 degrees, but that's okay. That's fine. But it's showing you that increasing atomic mass, and as you increase atomic mass, after we go from 19, we go to 23. So it's still increasing atomic mass, isn't it? Right? So let me get rid of all this. So no, I mean, again, that was increasing atomic mass from fluorine to sodium, except now we just put it down here. But if we read this table, like sentences, we go and this row, we go to the beginning of the next row, it's still increasing atomic mass. Yet the pattern of behaviors is repeating again, isn't it? We go from a red to an orange to a yellow to a green to a blue to a brown to a black. And this is called periodicity, right? This repeating pattern, it's periodic. It's kind of like days of a week, right? Days of a week is Monday or Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, and then the next week starts again with Sunday, Monday, Tuesday. So every 7 days, you start with a Sunday, or every 7 days, it's Tuesday to a Tuesday, or Thursday to a Thursday. And so same thing here. Every, so many elements, we go from a blue element, we go down, we go this way, we go from, let me back up. We have a blue element, then we have a brown, a black, then a red, orange, yellow, green, then a blue element again. So this periodic pattern keeps repeating. So that's one thing that Mendeleev noticed. And others of the time noticed too, but then Mendeleev did something a little different. When new elements were discovered, he could take them, and depending upon their properties and their masses, he could place them in the right spot in his table, right? So, like, here's potassium. Well, he knew potassium was going to go here, right? Because 35, 39, increasing order, but it's a red element, so it behaves a certain way, so it's going to go there. Arsenic, it's got to go here. Bromine is gonna go here because it's a heavier element, but it's gonna behave like one of those elements. Selenium is here, and in calcium he'd have to put here, right? Because it's an increase. Look, 39, 40, right? It couldn't go anywhere else. Increasing atomic mass. But the one thing that was really ultra cool about Mendeleev's table was he left blank spots where he didn't have an element, or maybe there wasn't a known element at the time, but he realized, like, look, there's a big gap between 40 and 75 in terms of atomic mass. Big gap there. There's some elements that weren't discovered. As a matter of fact, not only were they not discovered, not only did Mendeleev leave spots for them, but he also was able to predict what the behavior of those elements would be, and even named them. He even named them because he knew of the other elements around it in his organization that would tell him what these properties would be like. He knew that in this spot here, he called this Eka aluminum, because he knew that there was going to be a spot here of an element that behaved like aluminum, and because of the averaging of properties similar to what Dobereiner did, he was able to predict what those element properties would be like. And he did the same thing with this spot. He named this Eka silicon. And again, because he knew it was going to behave like carbon, like silicon, and because of averaging the properties similar to what Dobereiner did, he was able to predict what the properties of the element would be before they were even discovered. And then when they were discovered in Mendeleev's lifetime, they matched his predictions. And because of that, because there were other people who were organizing the periodic table, but Mendeleev was the only one to really truthfully and methodically predict these unknown elements. He was named the father of the periodic table. And it's undeniable. So, pretty impressive. All right, in the next lesson, we're going to learn how to do the predictions of unknown elements like Mendeleev did. We're going to compare those to the way Dobereiner did it, because obviously Mendeleev borrowed some of what Dobereiner had done.